So if you look at your wrist right now, there's a very good chance you're wearing a miniature computer.
Oh, absolutely.
Something that tracks your heart rate, buzzes when you get a text, and, well, eventually ends up in a drawer when the lithium-ion battery degrades a few years from now.
Right, yeah. I mean, it is just the reality of our current relationship with technology. We're so surrounded by disposable electronics, and we've
Yeah.
kind of largely accepted that the devices we interact with most intimately just have this built-in expiration date.
Which is exactly why the source material we are diving into today feels like such a stark, honestly refreshing contrast. We're doing a deep dive into a comprehensive guide titled Men's Watches, a beginner's guide to mechanical movements.
Yeah, and for those of you listening who already appreciate the aesthetic of a classic watch, or maybe you follow horology from a distance, our mission today is to really help you look past the dial.
Exactly. We want to shortcut your path to being a well-informed watch aficionado. So we are stripping away all the intimidating horological jargon to reveal the literal miniature marvel of engineering inside these timepieces.
It really is a marvel.
Okay, let's unpack this. What makes a mechanical watch fundamentally different from all the digital devices we're so used to?
Well, the clearest distinction is the absolute absence of electricity. Like, a digital or quartz watch relies on a battery to send a current through a circuit. It is, for all intents and purposes, a dead object until that current flows.
Right.
But a mechanical watch is an entirely physical ecosystem. It's powered completely by this incredibly complex system of gears and springs and levers that operate off of stored kinetic energy.
So before we even talk about which watch you should buy or the different styles, you really need to understand the heartbeat of the device. I mean, how does it actually operate and store that energy without a battery?
We have to trace the path of the kinetic energy, and that begins with a component called the mainspring. This is your central power storage. When a mechanical watch is wound, you are physically coiling a really long, thin ribbon of specialized metal alloy extremely tightly inside this tiny barrel.
Uh-huh.
And as that spring naturally attempts to uncoil back to its relaxed state, it exerts a rotational force.
I was actually trying to visualize this while reading the guide. Tell me if this analogy works. Is the mainspring basically like a tightly coiled measuring tape that desperately wants to snap back, but the escapement acts like a tiny dam, only letting that energy leak out drop by drop?
What's fascinating here is that your measuring tape analogy actually gets us halfway there.
Oh, just halfway.
Yeah, because imagine if that steel tape were coiled so tightly inside its housing that it could literally shear metal gears if it were released all at once. That is the sheer amount of tension we are talking about.
Wow. That's terrifying, actually.
It is. If there were no regulating mechanism, the watch hands would just spin wildly out of control. The whole watch would expend all its stored energy in about 3 seconds.
Right. So to prevent that violent release, the energy has to be transferred through a series of interlocking wheels, which is known as the gear train.
Exactly. The gear train multiplies the number of rotations while simultaneously stepping down that raw power. But the real ingenuity, the mechanism that acts as your tiny dam leaking energy drop by drop, is the escapement combined with the balance wheel.
And this is where the actual timekeeping happens, right?
Yes. And it's an amazing, purely mechanical transfer of kinetic energy. The balance wheel oscillates back and forth, usually beating 5 to 8 times a second.
That fast.
Yeah. And every single time it swings, it physically interacts with a component called the pallet fork. And the pallet fork unlocks the escapement gear for just a fraction of a second, letting a single gear tooth escape before slamming shut and locking it again.
Wait, so that tiny release of energy, that physical locking and unlocking of the gear teeth, that's the literal ticking sound you hear when you hold the watch up to your ear.
That's exactly it. It's literally the sound of machinery striking machinery several times a second.
That is wild. But wouldn't metal on metal striking like that just destroy the movement through friction pretty quickly?
It would, which is why watchmakers use jewel bearings.
Oh, right. The guide specifically mentions synthetic rubies, which, I mean, sounds like a massive luxury flex.
It sounds like a flex, but it's actually a highly functional engineering choice. Metal pivots turning inside metal holes will eventually wear each other down, no matter how much lubricant you pump in there.
Makes sense.
But a metal gear pivot resting inside a microscopic, donut-shaped synthetic ruby, which is incredibly hard and perfectly smooth, well, that can run for decades with minimal wear.
And the visual result of all this rapid, dual-regulated energy release is that hallmark, smooth, sweeping second hand, right?
Exactly.
Because a quartz watch just ticks exactly once per second, chunk, chunk, chunk. But a mechanical watch hand sweeps. It's moving multiple times a second in this beautiful, continuous gliding motion.
It really is mesmerizing. It elevates the watch from a simple tool to a miniature work of art.
Yeah.
But, it requires input.
Right. So now that we understand how the energy flows from the mainspring out to the hands, the natural next question for you listening to this is, how does that kinetic energy get into the mainspring in the first place?
And that brings us to the two primary categories of mechanical movements. You have manual wind and automatic.
Let's start with manual. This is the foundational old school approach. To power the mainspring, you actually have to physically pinch the little crown on the side of the watch and turn it.
You do.
Yeah.
And the guide notes that because there are fewer parts involved in a manual system, these watches can have a much slimmer, more traditional, elegant profile on the wrist.
But there is a trade-off.
A big trade-off.
Yeah.
It requires your active participation. If you forget to wind the watch every day or two, the mainspring completely uncoils, the balance wheel stops oscillating, and the watch just dies.
Right.
You then have to wind it back up and reset the time completely.
Okay, I have to push back on this a little bit. In today's world, where we actively design technology to be as frictionless as possible, isn't a manual watch just creating an unnecessary daily chore for yourself?
Well, if you look at it purely as a utility, then yes, it's an added task.
Yeah.
But we really have to consider the psychological appeal for collectors and enthusiasts here.
How so?
Taking 30 seconds every morning to wind your watch creates this deeply tactile connection. You are physically transferring your own kinetic energy into the machine to give it life for the day. It's an intentional ritual.
Oh, I see.
Yeah, you aren't just wearing a dead object, you are interacting with it. It honors classic watchmaking craftsmanship.
Okay, I can actually appreciate the romance in that ritual, but for those of us who might want the mechanical soul without the daily maintenance, the guide dives into the automatic movement, which is also known as self-winding.
Right. The automatic movement is just a brilliant evolution of the manual wind. An automatic watch contains the exact same core components, the mainspring, the gear train, the escapement, but it has a freely pivoting weighted rotor attached to the back of the movement.
And this rotor operates purely on gravity and the natural motion of your wrist, right?
Precisely. It's an asymmetrical weight.
Okay.
So as you walk or type or just move your arm throughout the day, gravity pulls that rotor down while your wrist changes angles.
Making it spin.
Exactly.
Mm.
This causes the rotor to swing in a full circle inside the case. And that swinging motion engages a series of reversing gears that continuously wind the mainspring for you, regardless of which direction the rotor happens to spin.
So as long as you're wearing it, it's just powering itself.
The clear advantage is convenience. You get continuous operation with regular wear without ever needing to touch the crown.
But there are downsides, right? The guide mentions it makes the case thicker.
Yeah, that extra rotor mechanism requires more physical space. And also, if you take an automatic watch off and just leave it on your dresser for a few days, it will eventually run out of power and stop running.
Which is why people buy those little spinning boxes.
Yes, watch winders. They're motorized display boxes that slowly rotate the watch to simulate wrist movement, which keeps the mainspring tensioned when you aren't wearing it.
Which really brings us to the elephant in the room, the big debate in the horological world. If mechanical watches, whether they're manual or automatic, require winding, require servicing, and can just stop running if you leave them on your nightstand, why not just use a battery-powered quartz watch?
To understand that, we really have to look at the side-by-side contrast that guide provides between quartz and mechanical, because they are two entirely different philosophies of engineering.
Let's break that down. A quartz watch uses electronic oscillators and a battery. It sends electricity through a tiny piece of quartz crystal, which naturally vibrates exactly 32,768 times a second.
It's incredibly consistent.
Yeah, and because of that exact frequency, it offers excellent, near-perfect accuracy. It requires minimal maintenance, basically just a battery swap every few years, and the cost is incredibly low.
Right.
On the flip side, a mechanical watch runs on that mainspring. Its accuracy is listed as good, but not perfect. It requires regular servicing, and it costs significantly more.
Objectively speaking, if a watch is solely a tool for measuring time, the quartz movement wins every single category. It is cheaper, more durable, and vastly more accurate.
So what does this all mean? Why would anyone deliberately choose the more expensive, higher maintenance, and technically less accurate option?
If we connect this to the bigger picture, we realize that human beings simply no longer need a wristwatch to know the time. I mean, you have a smartphone, your computer taskbar, a digital clock on your microwave.
That's true. Time is everywhere.
Mechanical watches survived the quartz revolution because they transition from being strictly utilitarian tools to being highly collectible wearable art. They are feats of microengineering.
That makes a lot of sense because you definitely don't pass down an old smartwatch to your kids. When the battery expands, it just becomes e-waste.
Exactly. These mechanical brands spend years perfecting the architecture of a movement. They utilize hand-finishing techniques on microscopic components, often on parts the wearer will never even see. They do it so these machines can last for generations and become true family heirlooms.
Wow. And once you appreciate that heirloom quality, the discussion naturally scales up. Like if watchmakers can build a microscopic engine that runs on a spring, how long can these miniature engines run, and what else can they do besides just pointing at the hour and minute?
Right, and this takes us into the highly competitive realm of power reserves and horological complications. Let's look at power reserves first.
Okay.
This simply refers to how long the watch will continue to run after it's fully wound, assuming it is taken off the wrist.
The guide breaks this down into tiers. So the standard reserve for most basic mechanical watches is about 38 to 42 hours, roughly a day and a half.
But modern engineering has pushed that baseline up, creating the extended reserve tier, which offers 60 to 80 hours. This is highly practical. It means you can take your watch off Friday after work, leave it untouched all weekend, and put it back on Monday morning, and it's still keeping correct time.
That's super convenient. And then there's the premium tier boasting 100 plus hours of power reserve, which is insane.
The engineering required to store that much tension without the spring buckling is incredible. It often requires multiple mainspring barrels linked together.
But where things get truly mind-bending is when we look at complications. The guide defines a complication as literally any function on a watch that goes beyond basic timekeeping.
Yeah, if a watch displays the hours, minutes, and seconds, it is fulfilling its primary purpose. Anything added to that is a complication, and some are purely practical.
Like the date display, just a little window showing the date. Or the day-date function, showing the day of the week, too.
But then we get into complications that are deeply romantic or just wildly technical. The moon phase, for instance.
I have to know, how does a watch physically track lunar cycles?
It involves a disc beneath the dial painted with two moons. This disc is attached to a gear with exactly 59 teeth. Once every 24 hours, the main gear train engages a finger that pushes that 59-tooth gear forward by one single tooth.
Okay, I'm following.
Because a full lunar cycle is roughly 29.5 days, a 59-tooth gear completes two full lunar cycles exactly as it rotates, showing you the precise phase of the moon through a small aperture on the dial.
That is just brilliant. It's literally math translated into interlocking metal. And then there's the chronograph, which functions as a mechanical stopwatch.
And the chronograph is exceptionally difficult to execute. You are essentially building a secondary watch mechanism on top of the base movement.
Oh, wow.
Yeah, when you push a button on the side, complex system of levers and a clutch instantly drops down to engage a secondary gear train, starting a separate hand sweeping to track elapsed seconds, minutes, and hours.
I was thinking about this. It's almost like having analog smartphone apps. But instead of writing lines of code, watchmakers have to cram physical gears for a stopwatch and a lunar cycle into a case the size of a coin.
And they have to do it without disrupting the main power supply.
That sounds impossible.
It's the crucial challenge. Engaging a chronograph creates massive friction. It drains the mainspring faster. If it isn't engineered perfectly, turning on the stopwatch could actually cause the main watch hands to slow down and lose time. Doing this correctly is the ultimate flex of advanced watchmaking.
It's unbelievable. Okay, so knowing how complex these systems are, strapping one onto your wrist and just walking out the door requires some thought. Let's move into the practical application. The buyer's guide, fashion, and maintenance.
Choosing a mechanical watch requires intention. The guide provides a